Okay, so if you recall from when we were in chapter 1, I said there were two main types of statistics: descriptive statistics and inferential statistics. Well, we did descriptive statistics in chapters 2 and 3, and then we took a little break for a while and we did probability theory in chapters 4, 5, and 6. Now we're starting inferential statistics, which uses sample data and descriptive statistics to draw conclusions, or in other words, make inferences about a population. So the first thing we're going to look at is that there's two types of inferential statistics that we'll concentrate on in this class. One is estimation theory, and that's confidence intervals, and that's what we're going to be doing in this chapter. And then after this chapter, we'll be looking at hypothesis testing. So estimation theory, it uses sample data to estimate an unknown population parameter. So it uses the sample mean to estimate the population mean. It uses the sample standard deviation to estimate the population standard deviation, and it uses the sample proportion to estimate the population proportion. Now, we're not saying I think the population mean is the sample mean, but that I think it's close to the sample mean. So we're going to define what close to means. Recall, I just said a minute ago, confidence intervals are used to estimate an unknown population parameter. So it has different components. The first component I wanted to talk about is the point estimate. It is the sample statistic that we are using to help estimate this population parameter. So it's the sample mean if we're trying to estimate the population mean. It's the sample proportion if we're trying to estimate the population proportion. And it's the sample standard deviation if we're trying to estimate the population standard deviation. Then we have some kind of margin of error. That's that idea of close to, where I said I'm not saying that the population mean is the exact same value as the sample mean, but I'm saying it's close to. And this margin of error is this idea of close to. The margin of error consists of two pieces: a critical value, which depends on this confidence level, and the standard error. If we're looking at confidence intervals for estimating the population mean, we're going to use the standard error of the mean, which we did see when we were in chapter 6. Now, there's also a confidence level associated with each confidence interval, and it's the most common ones are 90% confident, 95% confident, or 99% confident. And then this confidence interval is this point estimate plus or minus this margin of error. Single value or a point that's used to approximate a population parameter. Examples are: the sample mean is used to estimate the population mean. The sample proportion p hat, see that looks like a little birthday hat on top of the p, that's called p hat, and it stands for the sample proportion of successes, is used to estimate the population proportion of successes, which is just denoted with just a p. So true or false, point estimates are a very good way of estimating population parameters because samples do not vary from the population. Now think about this for a minute. No, that doesn't make sense. False. Point estimates are going to change. Our sample mean is going to change every time we take a different sample. So the confidence interval is a range of values which is used to estimate the true value of a population parameter. It's also called an interval estimate, and it's often abbreviated with a capital C, capital I. Is this value 1 minus alpha, often expressed as a percentage value? For example, 95%, which would be 1 minus 0.05. That is the proportion of times that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Let me explain that a little better with an example. So suppose I'm trying to estimate an unknown, remember it's unknown, population mean. So I take 100 samples and then create 100 different confidence intervals using the procedure I'm getting ready to teach you. So I have 100 different confidence intervals. If I'm doing 95% confidence intervals, what that's saying is out of the 100 different confidence intervals, 95 of them will actually contain the true population mean, but 5 of them are not. I do not know which 5 do not. So what I'm hoping with that 95% is saying that the one I have done is one of the 95 that actually does contain the true population mean, not one of the 5 that does not. And really, because the population mean, we're doing this because the population mean is unknown. We really do not know whether ours is one of the 95 or one of the 5. We're just betting on the fact that it's one of the 95. So this is also known as degree of confidence or confidence. This critical values, the sampling distribution of sample proportions can be approximated by a normal distribution under certain circumstances. We're lucky Minitab does the exact value or does this normal approximation. So I'll show you, you can see both when we use Minitab. Sample proportions have relatively small chances of being very extreme or falling inside these tails of size alpha divided by 2. So if I'm doing a 90% confidence interval, I have 10% left over. Then that 10%, that alpha divided by 2 is 5%. So my tails are what's on the extreme left and the extreme right are no more than 5%, half of 10. If we place 2 tails at the end of a normal distribution, then the sample proportion will fall into one of the 2 tails, and that's very small that it would fall into one of those 2 tails. So there's a chance of 1 minus alpha that the sample proportion falls between the 2 tails. That's the 95%. We're counting on the fact that that's a much bigger piece of the density curve. The z-score separating the right tail region is denoted by a z of alpha over 2. If the confidence level is 90%, then alpha is 10% and half of that is 5%. So it'd be a z of 0.05. It is referred to as the critical value because it separates the sample proportions that are likely to occur from those that are unlikely to occur. Value notations, we have the z of alpha over 2, and then that separates the upper tail, and the minus z of alpha over 2, because remember z is symmetric about the 0, is by symmetry the negative value, and it separates the bottom tail. Critical values are the values that are unlikely to occur. So values on that borderline or further down the tails are unlikely to occur. I'm going to show you how to do this with Minitab in just a minute. Okay, so the z of alpha over 2 is a critical value that is a z-score with the property that it separates the area of the alpha over 2 in the right tail of a standard normal distribution. All right, so let's see if we can find the critical value for corresponding to a confidence level of 99. So if 99% is in the middle, then the tails contain 1% left over, and the tails split that 1% half and half. So half of 1% is a half a percent. A half a percent, 0.05%, written as a decimal is 0.005. So I go to Calc, Probability Distributions, Inverse Cumulative Probability, Input, 0.005, click OK, 0.575 plus or minus, I think it's going to tell you minus 2.575, but by symmetry, it's plus or minus 2.575. Now that you know the confidence level, the critical value for a 99% confidence level, you never have to look it up again. Okay, so that's the confidence level for every 99% when you're dealing with Z's. And we can do the same thing for 95 and 90%, the other two very popular ones. Now the conditions for a proportion are it needs to be a simple random sample. My point estimate or my sample proportion p hat is equal to the number of successes in the sample divided by the total size of the sample. The binomial condition must hold, which means there has to be only two possible answers, yes or no, and each time I ask the question, that is independent, the answer is independent of the answer before or the answer after. And if we're going to do this approximation, then n times p hat has to be greater than or equal to 5, and n times q hat have to be greater than or equal to 5. We're going to see that the new Minitab 17 and Minitab 18 both do the exact method, so we don't have to do this normal approximation. But your book discusses the normal approximation, so I wanted to discuss it with you. Is that error that it's plus or minus that point estimate. So for p hat, it's called the maximum error of the estimate, and it is equal to that critical value times the square root of p hat, the sample yeses, the proportion of sample yeses, times q hat, which is the proportion of sample no's, divided by the sample size square rooted times that critical value. Remember, if the confidence level is 99%, that critical value is 2.575. And then the confidence level is plus or minus that margin of error. So let's look at an example. First, let's find the margin of error that corresponds to the given statistics and confidence level. If n is 800 and x is 200, we're looking for 95%. So I'm going to show you how to do it by hand, but then I'm going to show you a quicker way to do it with Minitab. So it's 0.030, because if I put 0.95, then I have 5% left over. Half of 5% is 2.5. 0.025 is 2.5% written as a decimal. I go to Calc, Probability Distributions, Inverse Cumulative Probability, Input 0.025, and I'm going to get 1.9 negative plus or minus 1.96. It's going to tell you negative, but by symmetry it's plus or minus 1.96. Then the 1.96 times the square root of 1/4 times 3/4 divided by 800 is 0.030. I'm going to show you a quicker way to do it with Minitab. I just wanted to show you that's how you would do it, using the formula on the slide before. The left endpoint, we take the point estimate, the 200 divided by 800, which is 0.25, and add and subtract that margin of error. Let's see how to do it with Minitab. It's so much easier with Minitab. So we're going to go to Stat, Basic Stat. Another menu drops open. Go to One Sample Proportion. You enter X as the number of events, and N is equal to the sample size. Click Options and check the box. Remember, there's a box there that dropped down that says either exact or normal approximation. The exact is better because it's exact, but the normal approximation is what the book is talking about. So I wanted you to be able to see both. Then you select your confidence level. It defaults at 95%, but you can change it to 90%, 89%, you can change it to whatever, and be sure that the alternative is set to not equal. All right, let's look at an example. Let's find the margin of error and the 95% confidence interval for if n is 400 and the number of successes or the number of yeses is 300. So we're going to write this stuff down, then we're going to go to Minitab, and we're going to try it together, right? So x is 300, n is 400. We're going to go Stat, Basic Stat, One Proportion. We enter in the number of events as 300. The sample size is 400. We go to the Options box and make sure we check Exact. Select that the confidence level is 95%. It defaults at 95%, so unless you change it, that's what it says. Okay, and it's going to tell you your confidence interval is that. Okay, now, if you want to find the margin of error using Minitab, the margin of error is half the length of this confidence interval. So if I take 0.7917 minus 0.7046, that gives me the length of the interval, and I want half of it, so I divide it by 2, and I get 0.04355. So my margin of error is 0.04355, and my confidence interval is 0.7046 to 0.7917. What that's saying is I'm 95% confident that the true population proportion of yeses to whatever question I ask those 400 people is somewhere between 70.46% and 79.17%. Okay, so using Minitab, it's really easier to find the confidence interval first and then go back and use the above formula to find E. Looking for a sample size given a specific margin of error. You need to use this formula. N is equal to that critical value squared times the p hat times the q hat over that margin of error, given margin of error squared. Now you use this if p hat is known. So what we're going to be doing is it's going to be 1.96 squared times, now we need to, let's go back to the numbers we had. All right, so we had the p hat was 0.185, which means q hat is 1 minus 0.185, which is 0.815 over E, and our margin of error is 0.05 squared. So you put that into a calculator and you get 231 something, which we round up to 232. Now the next one we're going to look at is confidence intervals for the mean, and the conditions are a simple random sample. We have a population standard deviation is known, the population is normally distributed, or n is greater than 30, then our point estimate is the sample mean. The population mean with sigma known is a z critical value times, remember the standard error of the mean? It's the population standard deviation divided by the square root of the sample size. That's standard error of the mean, which we saw in chapter 7. I'm sorry, chapter 6. Then my confidence interval is plus or minus the margin of error. Okay, so if we had to find the margin of error for a 95% confidence interval where n is 100, the sample mean is 95 and sigma is known to be 1, 2, 3, 4, 5. So the critical value for 95% is 1.96 times the standard deviation of 1, 2, 3, 4, 5 divided by the square root of 100. Put that into a calculator and you get 2419.62. Find the left confidence interval. We just take the sample mean of 95,000 and subtract the margin, and we get 92,580.38. I wanted to show you how to do it by hand just so you had a feel for what's happening, but we're going to let Minitab do this for us. Minitab to find the confidence interval for a sample mean. When the population standard deviation is known, we go to stat, basic stat, one sample z. We enter in the sample size, the sample mean, and the sample standard deviation. I'm sorry, the population standard deviation because it's known. Then go to options and select confidence level, 90, 95, 99, whatever you're asked to find. Be sure alternative is set to not equal. And you'll get the confidence interval. Okay, so let's find the margin of error in the 95% confidence interval for the following example. So we go to stat, basic stat, one sample z. N is 100, sample mean is 95,000, population standard deviation is 1, 2, 3, 4, 5. We go to options and select 95%. And we should get 92,580 to 97,420. Remember to find the margin of error. It's half the length of the confidence interval. So you take the upper limit, 97420, minus the lower limit, 92580. And then divide that by 2, and you get the margin of error is 2,420. Find the sample size for our confidence interval for estimating the mean. You use this sample size formula, which is different than the one we just saw a minute ago. And again, the samples must be integers, round up. So in this case, if we want to find the margin of error is 125, the confidence level is 95%. And sigma is 500, then we do the critical value for 95% is 1.96 times the 500 divided by the 125, and then square that number, and we get a number 61 point something, round up to 62. Now, if we're estimating mu and sigma is not known, the requirements are the sample still needs to be a simple random sample. Either the population is normally distributed or n is greater than 30. If n is less than 30 and the population standard deviation is unknown, then the t distribution is appropriate. like the z distribution, it's still symmetric and bell-shaped. It's a little wider. And most, remember with the normal distribution, 99.7% of all the data lies within plus or minus 3 standard deviations of the mean. About that same amount lies within plus or minus 4 standard deviations of the mean with the t-distribution. But it's still, it's very much like the normal distribution in that it's centered around 0. The difference is as n increases, which is known as degrees of freedom. So degrees of freedom for a t-distribution is sample size minus 1. As the degrees of freedom or sample size increases, the t-distribution is getting closer and closer to a normal distribution. So once you hit 30 or get very close to 30, then the critical values you would get, or the answers you would get with a t-distribution, are almost the same as the ones you would get for a normal distribution. The margin of error is that critical value times the standard deviation over the square root of n. And remember, when you're finding critical values, n minus 1 is the degrees of freedom. Interval is the sample mean plus or minus the margin of error. So to find the margin of error for a 95% confidence interval with n equal to 15 and standard deviation equal to 108 and sigma is unknown, well, the first thing we need to do is we need to find the critical value. So we go to Calc, Probability Distributions, T, Inverse, put in n is 15, or if they ask for degrees of freedom, it's 14. Again, remember, if 95% is in the middle, then 5% is left over, which is 2.5% on either side. 2.5% written as a decimal is 0.025. You put that in and you'll get a critical value. When you put that critical value into the formula of using 108 divided by square root of 15, you should get 59.81. Using Minitab to do all this, let's go straight and use Minitab, which is why I didn't go to a great detail to explain to you how to do it all by hand. We're going to go to Stat, Basic Stat, 1 sample T. Either enter in the sample data, which is n, sample mean and standard deviation, or sometimes you're going to have data to enter into the columns. Go to Options, select your confidence interval, be sure alternative is set to not equal, and you'll get your answer. So let's look at an example. So we have we go to Stat, Basic Stat, 1 sample T. N is 15. The sample, if it asks for degrees of freedom, then it's 14. If it asks for sample size, it's 15. Sample mean is 496. The sample standard deviation is 108. Go to Options and select a 95% confidence level. You're going to get the confidence interval is 436.2 to 555.8. To find the margin of error, it's still half the confidence interval. So it's the upper limit minus the lower limit divided by 2. The margin of error is 59.80. See, this is a much easier way to do it. That's why I kind of don't spend a lot of time teaching you how to do it by hand. I just want you to get the big picture. Between the t-distribution and the z-distribution, there's a chart on page 308 in your textbook that I would figure out a way to print out and have handy. All right, so the last confidence interval we're going to look at is estimating a population variance or standard deviation. The requirements for estimating either the population standard deviation or the population variance are: the sample needs to be a simple random sample, and the population must have normally distributed values even if the sample size is larger than 30. It uses a new distribution. So far we've seen the z-distribution, we've seen the t-distribution. Here's another one, the chi-square distribution. Okay, that's the formula for it. We don't really need to spend any time examining that formula. I'm going to show you how to do it with Minitab. And then you can either use table A4 to find values or Minitab. I think Minitab's easier. So in this chapter, degrees of freedom is n minus 1. Chi-square is not symmetric though, so you're going to have to find both the lower limit and the upper limit. With the z and the t, they were both symmetric about the 0, which meant all you had to do is find one, and the other one was the positive value of that. But with chi-square, you're going to have to find them both. So, and all values of chi-square must be greater than or equal to 0. The chi-square distribution is different for each degree of freedom. That's why Minitab's going to ask you for degrees of freedom. Remember, degrees of freedom is sample size minus 1. Two critical values separately. The table finds the area to the right, and so you have to do the first one you put in to find chi-square left. You do 1 minus alpha over 2, and then chi-square right is alpha over 2. I think it's good. We still have to do that, figure that out, but I'm going to show you how to do it with an example using Minitab. And then the confidence interval is, we don't really find a margin of error this time, so because it's not symmetric. So here we have that. But remember, Minitab's going to do all this for us. We don't have to find all these components by hand. Now let's concentrate on how to use Minitab for this. So to find the chi-square critical values, you go to Calc, Probability Distributions. This is where you went for binomial, Poisson, normal, and T, and uniform. And now we're going to go to chi-square. You enter in the area to the left of the left critical value, and then you enter in the area to the left of the right critical value. I'll show you with it. We're going to do an example. Next slide. Let's find the critical value for a sample of 22 values with a confidence level of 95. We go to Calc, Probability Distributions, chi-square. When we're finding critical values, those are values, so we do inverse cumulative probability. We enter in the degrees of freedom, which is n minus 1, which is 22 minus 1, which is 21. Now to find chi-square left, we do half of what's 95%, what's left over is 5%. Half of 5% is 0.025. So we enter in 5.025 and we get chi-square left to be 10.2829. Then you have to go back again to Calc, Probability Distributions, chi-square. And this time we're going to input what's to the left of, if we had 0.025 to the right, 1 minus 0.025 is 0.975. That's what's going to be to the left of chi-square right. And when you put that in and click OK, it tells you chi-square right is 35.4789. I think it's best if you stop the lecture now, write this example down, and then go to Minitab and make sure you can get these values while it's fresh in your mind. Interval, we're going to do it very similar to what we did with the Z and the one sample Z and the one sample T. So let's look at an example. Find a 95% confidence interval for IQ and lead group 2. So that's one of the data sets from the www.triolastat.com. I also have it on the portal for you. And you need to copy the middle group 2. So there's 22 subjects in group 2. You need to just copy just the full IQ scores, which is the last column. For just the, not group 1, not group 3, but just the middle ones in group 2, is 22 of them. Then take those numbers and copy them over into another column. The first thing we need to do is check normality. So I go to, remember, graphs, normal probability plot. I input those whatever column that those 22 subjects are in. And it turns out the p-value is greater than 0.05. So I know that the normal assumption holds. Then I go to stat, basic stat, 1 variance. I enter in the column of those 22 scores. And then I click OK, and I get that my 95% confidence interval to estimate a population standard deviation is somewhere between 11 and 20.4. We don't have to do those messy formulas that we did earlier in this chapter. It's just a table 7.2 on page 320 of your text, and you just find the look for the values that you're asked for it, and it's just look for the minimum sample size in that table. All right, so that's the end of chapter 7 material. Now it's time to do assignments in my math lab. Then you need to watch the lecture that I recorded for Lab 7, then download Minitab Lab 7, complete the lab, again as usual, either type in your answers and save as a Word document, or handwrite your answers and scan and save as a PDF. Do not tell you to take pictures. I cannot grade things when all I have is your picture from your phone. And then upload these one of these documents onto the portal under course assignments. right? So good luck. Please let me know if you have any questions on any of this material or on the lab, and I will get back to you. Thank you. Bye.